Imagine a robot preparing an omelet for you. This robot uses its vision, capturing RGB video data, to recognize the state of an egg, allowing it to assess the current situation and decide the next step. At this moment, the egg appears intact and raw. It hasn't been whisked or cooked. Based on this, the robot decides to crack the egg into a bowl. After performing this action, the robot reassesses the state of the egg to ensure it has been properly cracked and that the yolk remains intact. If the yolk is intact, the robot proceeds to whisk the egg as the next step. This example illustrates how recognizing multiple coexisting object states is essential for effectively understanding and executing procedural tasks, such as cooking or assembly. However, previous works typically assume that only a single object state change occurs in a video. These approaches focus on localizing the timing of the object's initial state, the action, and its end state. While this single state change assumption allows for the use of ordering constraints, which can simplify the localization task, it is insufficient for comprehensively understanding human activities. Many real-world scenarios involve multiple state changes or situations where an object's state remains unchanged, making this assumption inadequate for capturing the complexity of such interactions. Moreover, the single state change assumption fails to account for how an object's previous state influences the outcome of an action. For instance, consider the process of heating an egg, where its state changes from raw to solidified. The outcome can vary significantly depending on the egg's initial state, whether it is intact, whisked, or cracked. Therefore, it is crucial to recognize the coexisting states of the object, such as whether the egg is raw, intact, or whisked, to accurately model the events occurring in the scene. To address the limitations of previous approaches, we propose a new formulation for object state recognition as a multi-label frame-wise state classification task. In this framework, given a video as input, the goal is to determine whether each predefined state of the target object is positive or negative for every frame. This approach enables the recognition of multiple coexisting states and provides a more detailed understanding of object state dynamics over time. One major challenge of this task is the lack of labeled data for coexisting object states. Manually annotating complex state transitions and creating large-scale multi-label datasets is labor-intensive and time-consuming. To mitigate this challenge, leveraging transcribed narrations from instructional videos presents an intriguing alternative. Narrations often provide valuable insights into the events occurring in videos, making them a scalable resource for training models. However, these narrations tend to focus primarily on actions, offering limited detail about the specific object states involved. To address this, we propose leveraging the knowledge of large language models, LLMs, to infer the missing object state information by utilizing the relationship between actions and states. Additionally, we represent past states as descriptive context to account for their influence on future states. Our approach generates pseudo-labels for object states through 3 key steps. 1. Extracting actions mentioned in the narrations. 2. Using the past state and the current action to infer and describe the object's new state. 3. Accumulating past state descriptions to derive comprehensive object state labels. We then train the object state recognition model using these pseudo-labels while employing error correction techniques to improve their reliability. From now on, we will explain the details of how to create object state pseudo-labels and how to train the model using them. To create object state pseudo-labels, we follow a 3-step process. 1. Extracting manipulation actions. We first segment the narrations into smaller chunks and input them into the LLM to identify all manipulation actions occurring in the video. 2. Describing resulting states. For each inferred action, we use the LLM to generate a description of the resulting state of the target object. To ensure accuracy, the previous state description is provided as context when generating the new description. 3. Determining state positivity. Finally, we determine whether each state is positive, negative, or ambiguous at each point in time. For this step, all past state descriptions are input into the LLM to incorporate contextual information about previous states. This approach helps the LLM make more accurate inferences, even when the available information is limited. Using the timestamps of the narrations, we assign the inferred labels to specific frames with the help of off-the-shelf VLMs. After obtaining the pseudo-labels, we use them to train a multi-label object state classifier. However, the pseudo-labels are often incomplete due to missing actions or misalignment with the visual content. Training the model directly on these sparse labels can result in incorrect context learning, as the incomplete data may misguide the model's understanding of object state transitions. To address the issue of sparse labels, we apply a self-training strategy using an ensemble approach. Initially, we train 2 teacher models based on the sparse pseudo-labels. One is a temporally aware model, and the other is a frame-wise model. These models complement each other in their ability to infer object states. By combining their outputs through ensembling, we generate dense soft labels, which are then used to update a set of student models. After updating the student models, their parameters are copied back to the teacher models, creating a cyclical refinement process. Through this iterative approach, the pseudo-labels are progressively improved and the student models become more accurate. At the end of training, we only retain and use the student temporally aware model for final inference. To evaluate our method, we developed a new dataset called the Multiple Object States Transition, MOST dataset. This dataset includes over 150 minutes of videos showcasing complex transition patterns across various object states. We annotated approximately 10 states for each of the 6 object categories, spanning a diverse range of domains to ensure comprehensive coverage of object state transitions. We compared our method against strong zero-shot baselines, and the results highlight the effectiveness of leveraging LLM-generated pseudo-labels for training. We also conducted ablation studies to analyze the key components of our method. The results demonstrate that both considering past states in pseudo-labeling and implementing self-training schemes have positive impacts on recognition performance, contributing to the robustness of our approach. Here are the qualitative results, showcasing the performance of our method in recognizing and predicting object state transitions. These examples illustrate how our approach effectively captures complex state changes, highlighting its ability to handle real-world scenarios with coexisting and evolving object states. In summary, we have proposed a novel approach to object state recognition, formulating it as a multi-label frame-wise classification task to effectively capture coexisting and evolving object states. To reduce the reliance on manual annotation, we utilize the knowledge of large language models, generating pseudo-labels from narrations. This approach incorporates context-aware pseudo-labeling, leveraging past states to improve the accuracy and robustness of the generated labels. To evaluate our method, we introduce the Multiple Object States Transition, or MOST dataset, which contains over 150 minutes of annotated videos showcasing complex object state transitions. Importantly, this dataset and related resources will be made publicly available to encourage further advancements in this field.